In this video, we're going to deduce the structure of an unknown molecule, C5H10O2. So we have the NMR as normal, and we can see that there is between 10 and 12 a peak, and we've got one right down here. So straight away, though, I'm going to look at the molecular formula. I think I've got two oxygens. What am I going to make from two oxygens? Okay, right, okay, ester carboxylic acid should come to mind, okay? So ester is not going to be indicated because there are no hydrogens on those oxygens in the ester, but carboxylic acid is shown because it's a hydrogen on the carboxylic acid, and that comes out between 10 and 12. So you've got 10 and 12 here, a singlet with a 1 by it, which is very characteristic of a carboxylic acid. So if we move along here, we can see there is also another characteristic peak, which is a singlet here, again with a 9. So if you look at that 9 and think, what is that divisible by? Well, that's divisible by 3. That means, think of it, CH, CH2, CH3. Well, the CH3, 3 hydrogens, can be divided into 9. So that probably is 3 CH3 groups. Now, let's put that into a table, as we normally do. Chemical shifts, peak splitting, relative peak area. Okay, and we think that there are CH3s, and we think there is a carboxylic acid. Before we do that, here's the hydrogen environments. We've got 2 of them, and let's explain one of the peaks in terms of its peak splitting. So n plus 1 is 1. 1 minus 1 is 0, so we have 0 hydrogens on the adjacent carbon. And also remember, the carboxylic acid, you cannot couple peak split through that oxygen on the carboxylic acid, which is why it's a singlet. Now, we think that's a CH3, and we think that's 3 CH3s. We also think that that's a COOH. We'll do the normal check that we do, which will have the molecular formula, and then bring that down and see what we have remaining. Well, we have a carbon remaining. Well, that kind of makes sense, because if we've got 3 CH3s, the 3 CH3s are probably bonded to that carbon, and that carbon has no hydrogens on it. Okay, so, and that would mean that if they're bonded to a carbon with no hydrogens on, okay, they would come out as a singlet. So that kind of makes sense. But let's have first, before we go on to do the structure, let's have a reminder of D2O. So if I add D2O to this, and I just shake this substance with a bit of D2O, the carboxylic acid peak will disappear like that. And I'm just doing that to remind you, because we have this carboxylic acid, which is one of the groups that reacts or does proton exchange with D2O. Now let's bring it back, okay, and then move this to the side and start doing the structure. So the structure itself, we thought we had a carbon with 3 CH3s around it. So there is your CH3 around the carbon, and the carbon has no hydrogens on it. Well, that means that that carbon is bonded to something else that isn't a hydrogen. We also know that we've got a carboxylic acid. Well, that carboxylic acid has no hydrogens on it at all, okay? And it would mean that this carbon is next to this carbon here has no hydrogens on it at all because it's bonded to a carbon. So that would make sense. And there you have your carboxylic acid. So we've taken our 2 groups, we've taken our 3 CH3s. All of those are, because of symmetry, they all come out in the same hydrogen environment, okay? And because of our relative peak area of 9, we worked out that there's 3 CH3s there. We had a spare carbon, we stuck it in there, and we had our carboxylic acid. Well, let's just finish off and just say, right, okay, they are connected to a carbon with no hydrogens on. So I would see a singlet, and it would have a relative peak area of 9. For this one, I would see a singlet this time because the hydrogen does not couple through the oxygen. The oxygen blocks it, and it would be a singlet with a relative peak area of 1. And that is how you recognise a carboxylic acid and a group with 3 CH3s around it. To summarise what we've gone over here, if we have 2 oxygens, then always check for that carboxylic acid peak. If you don't see it, could be an ester. Okay, and the peak will look like this, with a slightly broad bottom and with that 1 by it. Again, the only time you will see where that has a 2 by it, for example, is if you had a symmetrical dicarboxylic acid, but they're very, very rare. Now, we also looked at a singlet with a relative peak area of 9. Okay, that 9 signified these 3 CH3 groups around that central carbon. That's usually bonded to a nitrogen or an oxygen, or in this case, carboxylic acid. And it's symmetrical. And then there is our molecule that we have right there showing that symmetry.